Hello everyone, this is Spencer Snolling from Hydromantis, and I'm glad that you were able to join us for today's webinar. We're going to be talking today, whoops, I lost my slide. We're going to be talking today about optimizing chemical dosage by using GPSX, and specifically we're going to talk about how to set up chemical dosage units in your model, how to install some controllers, and a few ideas and important things that you need to know about how those are modeled and how to get them set up properly. So my name is Spencer Snolling. I'm VP of Product Development here at Hydromantis, and I'm glad you were able to join us. So the agenda for what we're going to do today is to first go through the various different types of chemical dosage models that we have available in GPSX. I'll talk about typical applications, and I've set up a few demonstrations today that I think are typical of the way that I use the chemical dosage and the controllers in GPSX, and the way that I know several of our clients do as well. I'll talk about the controllers, the PID control loops, how to tune them, how to set up the various important parameters and things to keep in mind. And as always, and that's the part I enjoy the most, is doing the actual desktop demonstration. So as per usual, we'll have 2 or 3 times I'll bring up my desktop, we'll have GPSX up and running in some layouts, and you'll be able to see things running and demonstrate those important parts of these models. And as always, I'll be around to answer any questions that you have as we go along. So if you've been to our webinars before, you know that there is a questions panel as part of your GoToWebinar dashboard. So you can pop that out and open it up and type your questions in there. And then I will usually wait till we get to the end of the webinar. I'll have a few words about some upcoming things we have going on at Hydromantis, and then I'll take some time to answer those questions. All right, let's jump in. So the chemical dosage models in GPSX are a little bit diverse. They're used and implemented in a couple of different ways. So many of the chemical reactions that are an important part of the activated sludge process have been included in the biological models in that matrix of process equations for quite a few years now. And in fact, way back with ASM2D, there were a couple of rates included in that model for the formation of metal phosphates and metal hydroxides. So we've continued on with that type of process where we have precipitation reactions that are part of our overall model matrix. So, and therefore, you will find that those types of chemical equations, those types of processes and precipitation and whatnot will take place in your model, any place that there is the Mantis 2 model happening. So any place you have biological reactions going on, such as these objects that you see here, all the regular activated sludge ones, the biofilm ones, the digester, struvite recovery, all of those types of ones where we have the actual matrix of equations being solved. So you can at any point actually plot how much precipitation is happening by going to the output menu called Mantis 2 rates and pop up this part of the menu. Mantis 2 rates contains all of the rates that are going on as we solve them, the amount of material that's being converted from one form to another over time, and it's broken out by the rows of the matrix. And so here I've just highlighted the fact that there are these precipitation parts. They're generally down towards the bottom of the matrix, so you have to scroll to the bottom of that menu to find them, and you can find out here how much precipitation is going on in any one reactor in your layout. And if you see a negative number, by the way, that's indicating that that might be a little bit supersaturated and it's now being dissolved back into the liquid. So in GPSX, we have a couple different types of objects that have been designed to take advantage of not only those precipitation things, but any of the other biological reactions that are going on that react to changes in the chemistry. So first of all, our influent models have a couple special ones here that are shown in this area here. They're found in our regular influent portion of our process table. And these models are there to set up an influent in a way that would work as a chemical dosage. We also have another object that's found in the primary treatment group that's called inline chemical dosage. And this one is a little bit different. It's not an influent. It doesn't add any flow into the equation, but it's a flow through unit where we are going to be adding something, usually a metal in this case, that is going to become part of that flow, and there's going to be some reactions that happen there. So the question, first of all, just to get everything started, is how do I know which one of those objects to be using for any particular time? So the answer to your question is what am I actually dosing? If I'm dosing carbon, if I'm dosing something like methanol, so a COD form, or if I'm dosing a nutrient such as some form of nitrogen or phosphorus, then you want to be using these objects here that are found in the influent menu. The COD chemical dosage object, the nutrient dosage object, those are the ones when you're dosing those types of things. If I'm dosing for pH control, if I'm dosing an acid or a base, we have special ones that are also found in the influent menu, the influent portion of the process table. And then also, if you're going to be dosing metals such as iron or aluminum for doing phosphorus removal, then that's where you use that inline object that I have. So if it's carbon, nitrogen, phosphorus, or an acid or a base, you look in the influent panel, or you look in the primary treatment one if you're going to be dosing a metal. All right, so I'm going to take some time to go through those and show you the various different kinds of chemicals that we have configured for you to be able to dose, and talk a little bit about the various ways that we do this. So first of all, let's pick the most straightforward, the most commonly used one, and that's where we are going to be dosing a carbon source for the improved denitrification. So in this case, it's the COD object. We're dosing COD here, and we have lots of different forms of the COD that can be used. And you can pick whichever one you want, and various parts of this menu will become highlighted, and you can have access to things like the purity of the solution and so on. So you can see here we have acetic acid and propionic acid, methanol, molasses, glycerol, and then mixed substrate. And mixed substrate is the one, by the way, that you should use if you're dosing some sort of synthetic COD product, such as micro C. We get a lot of technical support questions asking about how do I set up a synthetic or a commercial product dosage for improving denitrification, and this is what you want to do. Pick that COD object and set it to mixed substrate, and then you can specify the COD. We have a good set of default parameters there, but also the amount of flow going into your particular system. So what GPSX does then in this case is that it makes an influent object. It's flow coming into this plant that's leaving that particular object. Usually, of course, it's very concentrated, so it's a small amount of flow. But then you have a series of concentrations just like you would in any influent object, and they're pretty much all set to 0 except for the relevant things that are for this particular dosage. So I just plotted a little bit of the state variables that are from this particular object. You see that most of them are set to 0 for the different types of substrate except methanol, which is of course what we were actually dosing. And there's your 100% pure methanol COD of just over 1 million milligrams per liter. So it's the same thing with the nutrient dosage object and the acid and base ones as well. You go in there, you pick up from that chemical menu, you choose the kind that you want to be dosing. So you can see here that we have hydrofluoric acid, we have urea and other forms that can dose either nitrogen or phosphorus or both, and those are typical for places where we would want to add nutrients in a nutrient limited situation such as an industrial wastewater source. We also have acid and base dosing, as I mentioned, for pH control. Again, the same thing. We have hydrochloric acid, we have sulfuric acid, and for bases, things like sodium hydroxide and calcium carbonate and so on. So again, pick the particular thing that you're looking for, set the appropriate concentration, and then you can set the flow rate to do the dosing. All right, so let's jump right in and take a look at one of those. This here is a very simple, straightforward biological nutrient removal plant that I set up. It's doing nitrification and denitrification. So this is an MLE plant. It's very simple. This is 2.5 NGD, and it's reasonable types of performance here. I set it up to be a very typical application, and we've included this COD dosage object. So that's found right up here in that influent panel. So I dropped one down here. And if I right-click on it, as I mentioned before, you can go to the composition menu and you can go to the feed chemical details, and this is where you select from this menu. So I've selected methanol already. I'm just going to leave it at the default concentration settings. And then I can set the flow rate that I want to use. Now I'm going to leave it at 0 now because I want to play around with it on the slider when I move over to simulation mode here. So the first thing I'm going to do is actually just run a simulation under our default settings here, and I'm just going to let this solve to steady state, and we will click on this effluent tab here and we can take a look at the performance of this plant. So it's been sized properly. We can see the effluent TSS is 11. We can see that it's fully nitrifying. We have ammonia of less than 0.1. And we have nitrate, of course. It's doing some denitrification. We had about 25 milligrams per liter of nitrogen coming into that plant. Our total nitrogen leaving the plant is 11.9. So keep that in your mind, 11.9 milligrams per liter of effluent total nitrogen. So I put the flow rate of that COD dosage up here where we're adding that methanol. That's available to us to play around with right here. So first of all, I'm just going to add a little bit. Just keep that 11.9 in your head. We're going to just add that. So now that's a continuous flow of dosage that's going into the anoxic zone of that particular MLE system. And then we solved it again. And we can see here, well, it dropped down a little bit, about a milligram per liter. If we push that up again, now here we can see that it will reflect that new carbon dosage that is no longer being carbon limited in the anoxic zone like it was previously. We can get a little bit better performance, and we can see now we can get down from 11.9 down to 8, and with dosing a bit of methanol. So, and of course, this is still a regular soluble substrate, and it is still affecting all of the other things that are going on in this particular system. We have a specific biomass type here, methylotrophic biomass, that it's doing its job, but that soluble substrate is available to other biomass types too, and it also could theoretically make its way out of the effluent. For example, if you completely overdose this, and then let's just solve that again. Here I doubled that chemical dosage of the methanol there. We'll just let that converge to steady state. And we can see now we've got total nitrogen down to 7.8, so we didn't get a lot of improvement over half of that dosage. But we can see now our BOD, which was previously 3.5, is now 30. So we've now kind of overwhelmed that system with some soluble COD and gone well past the point of getting any good usage out of that. So that's a good way to sort of set this up, and you can do some optimization there. You can try and find out what is the best dosage rate for my particular setup here, and I can start doing things like optimizing the size of the anoxic zone versus the amount of carbon that I'm adding and play around. And if you attended our last webinar, which was on the optimizer feature of GPSX, you could actually take those two parameters and put them in the optimizer and let it find what those optimal parameters are for you. Okay, so let's go back to the slides. Okay, so that's the way that you use those type of influent type of chemical dosage objects. And now we're going to talk about the inline dosage object. So this is one where the flow is going to flow through this particular unit. It doesn't do anything to change the flow. We are just going to be adding in a metal. So in this case, for this particular unit, you can add either alum or ferric iron into this system, and it is going to go ahead and do the precipitation of phosphorus and a few other things. And when you're dosing, it's important to remember here that you're dosing the actual ferric ion. So if you say, I know exactly for my particular dosage, you're trying to calibrate to a known plant, and I'm dosing a certain amount of ferric chloride, the amount that you should be entering in here is actually just the iron portion of this. So you may have to do a little stoichiometric calculation to get from the total amount of compound that you're using to just the iron mass that's going to be going in. We'll give you a heads up. We're going to change that in the next version of GPSX so that you'll be using the total amount. However, right now you're looking at using just the ferric ion by itself. And you can dose it in two different ways. You'll see mass and concentration based here. So what that really means is when you're doing the mass base, it's per time. I'm just putting in the total mass of iron per time, and that's divided up and put in continuously, or you can do it per unit flow. So in other words, I'm going to dose a certain mass of iron per cubic meter of flow that goes by, and that allows you to maintain a constant concentration even if the flow goes up and down. So now this is a zero volume object. All of this chemical reactions take place really quickly. So we assume that all reactions happen instantaneously and nothing is going to be, there's no sort of residual reactions going on in the downstream objects. So therefore there's no real volume associated with this. It's just an instantaneous transformation that happens as it passes through that particular object. Should notice too, though, that we also are removing, in addition to the phosphorus, colloidal COD, soluble inert COD, soluble organic nitrogen, In that case, it's really reflecting the coagulation that you would see that would be associated with dosing iron. So we're going to remove a little bit of COD around that way too, and you would actually also see that reflected in the COD balance as you move along. You can actually calibrate that part of the model as well. So in Mantis 2, while you're doing this type of dosing, you have to keep in mind that the phosphorus removal itself is pH dependent, and the amount that you're adding is also affects the pH too. So within the model, we have a solver there to figure out how that's all going to work. And you can calibrate the model by adjusting things that are found on the flocculation and P precipitation parameters menu. This contains a bunch of stoichiometric ratios, which are actually pretty well known. You probably don't want to adjust those. However, you can adjust things like the solubility product here. So that's a way that you could, if you have performance at your plant that is maybe a little bit inefficient for one reason or another, you can make adjustments and calibrate the performance of the model to your known data by making adjustments to that solubility. So because what's really happening is for all that flow that's coming in and the amount of phosphorus that's coming in, we do a solubility calculation here, given the amount of metal that's present, the amount of phosphorus that's present, and then we determine, is that enough to meet that phosphorus solubility product, and if so, which one of the things is the limiting step here? Are we limited by the metal? Are we limited by the phosphorus? And there, from that point on, we go through the stoichiometric evaluation to figure out how much of sludge, new particulates are being formed, and then that becomes part of the stream that continues on. Okay, so let's take a quick look at that then. So I'm going to switch over to my next demonstration layout. So this is a very similar type of plant, about the same size, slightly different influent characterization. And in this particular case, I'll just show you what this looks like. I've put in actually two dosage points in this particular one. One that's dosing right as the influent comes into the plant, so that can be collected, the material that precipitates out can be collected and wasted in the primary clarifier. And then another dosage point after the biological tank, and that would be collected up and taken out in the WAS. So I didn't model the solids handling portion of the plant, but that's also a really interesting thing to do with our software, is to model how that phosphorus balance works through the solids handling side, and in fact even trying to recover that phosphorus. So just quickly to show you again, open up that model input parameters menu. You can set the chemical dosage here. This is where you pick the type of metal that you're adding and then the amount that you're adding. So right now I'm going to leave these so that they're in the model but not dosing anything by default. And let's just run it once. Let that converge. So we're going to let this just be a steady state solution here. We can see the soluble phosphorus coming out the back end of that plant is 4.78. So let's call it 4.8 milligrams per liter of soluble phosphorus that is available. And just to highlight how this solubility issue works, I'm going to add a very small amount of metal here. And you can see here that has practically no effect on the amount that's out there. So, but if I start to put that up, we can see the effect. This is now dosing and just at this particular point in the process here. And now we've knocked that 4.8 down to 2.3. And then, I can continue to add here. If I was also plotting the sludge production, we would see an increase in the sludge production as well, because we're now producing a lot of particulate solids. We can get down to 1.9 here now just by adding that. And you can do a number of optimization strategies now with having two dosage points. We could actually even improve a little bit by adding some more up front there as well and get that even lower down to 0.05. Those are ways that, again, you can make those changes. You can do those optimizations manually yourself by investigating the performance of the plant. I will mention at this point, too, that, of course, you can overdose your phosphorus removal, and that will be reflected in the biological activity in the plant. So all of our biomass growth equations do show that phosphorus is required as a nutrient. So, and there's a half saturation coefficient that controls how sensitive the biomass is to that presence of phosphorus. So if you have a lot of dosage up front, you take out all the phosphorus, you will find that your biological activity will be very much impacted, and it will not allow you to see that growth. So that's actually an exercise and a couple of teaching exercises that I've made in the past that I've found very interesting, and it's quite easy to study using the models. Okay, back to the slides. And next, I want to talk about how you set up an automatic controller for your dosages. So this is actually very handy in two different ways. One of them is that you can, of course, model a different type of control system for your chemical dosage at your wastewater treatment plant and study how that would work and optimize that and so on. Quite frequently, though, well, if you're doing a design of a plant or you're evaluating a design or an upgrade, I don't want to have to go and adjust my chemical dosage every time I change the influent loading or every time I change some aspect of the plant. It's very nice to be able to just have a controller on there. I want it to do its job to make sure that it's meeting the requirement of the effluent phosphorus, and I just want it to report back to me how much dosage was required to make that happen. So each one of our influent type objects for dosage shows this flow controller menu, and if you pop that open here, you can turn on the controller. You have to specify the name of the variable that it is that you're trying to control. So in this case, this is total nitrogen in the effluent. And I won't go into all the details about how you set up PID control loops. That we actually have another webinar, and some of our tutorials are all based around how to do that. Same methodology there as what's being applied here. You type in the cryptic variable name of the thing you're controlling. Here's our set point, and we would have to hit into this more button and go through all of the tuning and so on to get that set up. An inline dosage object doesn't itself have a PID control loop, but as you may know, in GPSX we actually have some free-form open controllers that you can specify just by going to the process control panel. You can see all these different types of things that can be used to control wastewater processes, and the PID controller is the first one on that list, so you could drop one of these in your layout. Specify the dosage as the manipulated variable, specify the effluent phosphorus as your control variable, and move on from there. Okay, so let's just show you a quick example here using a base dose with a controller in order to manage pH. And what I'm going to do is actually use this nitrification pH example that's actually part of our sample layouts menu. If you go here, actually I should show you where to find that. If you go here, sample layouts, and then if you go under the process analysis examples here, you can see pH control during nitrification. This is the example that I'm showing you right now. And in this case here, it's just a nitrifying plant, a CSTR completely mixed tank, and we have an alkali, a base feed here coming in. And if I open that up, you can see the details here. We are adding sodium hydroxide to control the pH. And so that gets mixed in with the influent as it goes in. So in order to show you this in an interesting way, we've done a little bit of a dynamic change here. So I'm going to run this simulation one time here, and we can see that we have the ammonia nitrogen. It goes up and down during this 1 day of simulation. It goes up and down quite a bit. So what this is really showing us is that this plant is undergoing a change in the loading, and therefore a change in the amount of nitrification that is going on in this particular plant. And of course, you know, as you nitrify more, you consume more alkalinity, and that is going to have an effect on the pH. Now, this particular example we set up with an influent that's just a little bit light on alkalinity so that we could have a nice response to look at. So we can see here that we're sort of teetering on that edge of not having enough alkalinity here, and it is having an effect. In red here is the pH in this bioreactor. We can see here at the beginning of the simulation, it starts out at 7.2, and then it drops down below 7. That black line is 7. Gets all the way down here to about 6.7. So it drops about half a pH unit as it goes through this particular day. And that is due just to keeping everything else the same, just to the fact that we're doing more nitrification during the middle portion of the day there. So I could maybe just put up a constant amount of base here of sodium hydroxide in order to keep that sort of manageable, keep it a little closer to 7. But what we've done here is we've actually set up the control system by, I've made a scenario here, and if I go to the flow controller menu, we can see we've turned that on. We're controlling pH in that completely mixed tank, and we're going to try to keep it at a pH of 7. And as I mentioned, you're going to have to go in here and make some adjustments to the tuning parameters. So this is again part of what it's like to add PID control loops to anything in GPSX. So, but I'll just mention it again here. We've changed the gain and the integral time and the sampling interval. This is a really important parameter here to keep in mind too. Basically, it's the controller effect of the control variable. So it's essentially all we're asking here is, do the manipulated variable and the control variable work in the same direction or in opposite direction? So in this particular case, if I increase my flow, how does that affect the control variable? So if I'm increasing my flow of base, that is going to drive my pH up. So therefore, this needs to be on because they're moving in the same direction. If I was dosing an acid, that means, of course, more acid means a lower pH. So therefore, they would be moving in the opposite direction, and this would have to be set to off. But I'm using a base. They both go in the same direction, so that has to be on. And I'm going to run it with the controller on. So instead of dosing 0 base like we were before, now the controller is taking an effect. So instead of going way down here to 6.7, you can see now that it drops down to the set point of 7 and it kind of hangs out there, and then that controller is doing its job properly. And in fact, we can actually take a look here at the amount of alkali or amount of base that was added in order to make that happen here. So this is in meters cubed per day, and it went up and back down again. And that is just completely having this unit add based on what the pH was in the tank. And of course, like any BID control loop, there's a little bit of lag, and the tuning is important and so on. Okay, so that's how you do pH control in GPSX. Okay, a few final thoughts here, just a few tips on setting these kinds of things up. So back now to talking about doing COD dosage for denitrification, for example. I suggest you use the dual inlet plug flow tank here when you're doing those BNR type systems and you're setting up a bunch of reactors in series. Normally, as I'm sure you know, you stick the influent into that connection point there, and you connect your recycle, your RAS line back up to that lower connection point. And then that extra one is actually specifically designed to be used for dosing things like methanol or acetate. And so those go in there, and you'll note on the operational menu of these plug flow tanks that there is the opportunity to do some step feeding, and that's found at the very bottom of the operational menu. And you'll see here influent number 2, that's the one that is that upper connection point. That's where you can specify how you want to assign or how you want to divide up and those tanks in the flow that's coming in from your chemical to those tanks that are in series. So for example, by default, right now 100% of that goes into the first tank and nothing goes into the later tanks. And so meaning here that all of that chemical dosage that would be coming in here is going to go in that first tank. And that's the way I had it set up during that MLE portion, because of course the first tank is the one that is the anoxic zone. So that's just an example of a very useful setup, and you'll notice that actually many of our objects have 2 connection points like this on the front end. One of them is designed for the flow that's coming from the previous upstream object, and the other one is designed to be able to very conveniently add something like COD dosage. So as we talked about doing those PID controllers, the PID loops on dosage controllers can be a little bit tricky to tune. The chemical reactions, of course, are themselves very fast. So if you're doing an acid dosage type of controller, your controller needs to be tuned sort of in one way. However, if you were doing a controller, say for example on methanol, you would probably find that you'd have to have a much different type of controller, because of course it's not the reaction, a chemical reaction, it's the biological system reaction to the addition of some methanol. So that, of course, is a function of the biology. So it's slower. It's also completely a function of the SRT and the temperature and many other things. And so therefore, you'll find that that's sort of a different approach that is required. So, and also when it comes to chemical dosages, that's often completely proportional to the size of your plant, to that influent flow. So therefore, you may find going from one particular model of one plant to another particular model of another plant, you may need a different tuning parameter, a different gain, because if your plant was 10 times as big, your dosage is going to be 10 times as big, so therefore your gain probably will have to be adjusted as well. So try out the gain value on those controllers at different orders of magnitude, just to try and make sure it's doing the job, and getting it sort of quickly to the set point, but not overshooting too much. And last thing I'll mention here is that all of the chemical dosage, so that is things like the COD, methanol or micro C, the nutrients, all of the acids, bases, and all of the metals, all of that stuff is included in our automatic operating cost analysis. So you can specify the costs of, a pound of ferric chloride if you're going to be adding it, and then that will be automatically included to all of your simulations. And as you may know, if up on the top of the output side of simulation mode, we have all these buttons for adding and managing your information, and this very last one, this is new to version, the most recent version of GPSX, is this new operating cost button. So when you hit that, you get a large detailed analysis for each one of the objects, and you can get an overall plant analysis. And so this example is from one of the examples that's in our sample layouts menu here, and you can see that this chemical dosage cost, this portion of the pie of the overall cost of operating the plant, will be calculated from the numbers in those various objects that we've been talking about today. And you can set up with a different cost for each type of chemical as well. Okay, so just concluding, GPSX has several different ways to set up and dose chemicals for various types of processes depending on what you're doing, and a number of different PID controllers that can be put in there and incorporated in, and you need to make sure you got your tuning set up properly, and sometimes those controllers will be there and that will actually be the focus of what you're trying to do as part of your optimization, or maybe you just kind of want to have you just want to change what the degree of freedom is in your design. Just let that thing dose whatever it needs to dose in order to get the job done, and then I'll just keep an eye on how much it's telling me I need. And that's obviously one of the most useful aspects when you're using GPSX for design.